Well, good day, everyone, and welcome to another session in this year-long series of leading IEEE electron device luminaries, which is jointly organized by the Electron Device Society Delhi chapter and the Department of Biotechnology's Star College Students program at the Upadhyaya College and the National Academy of Sciences India Delhi chapter. This year-long series by the EDS Luminaries is part of the 75th anniversary of the transistor invention. And today we have with us Professor Yue Kuo, who's a Joe M. Nesbitt Professor at Texas A&M University College of Engineering. And he'll be talking to us today on an interesting topic, plasma-based thin film technology in fabrication of nano to giga-sized electronics. He's a fellow of IEEE, and he received his doctorate in engineering science from Columbia University in 1979. He served in industry, that is IBM DJ Watson Research Center at Yorktown Heights, New York, and Data General Corporation Semiconductor Division at California for about 20 years. He has conducted fundamental and applied research on semiconductor devices, materials, and fabrication processes for advanced ICs, thin film technologies, and optoelectronics. His pioneer works on plasma etching and depositions have been used in worldwide productions. In addition to papers, books, and patents, he has served as an editor and an editorial board of high-impact journals. He is the founder of the world's longest continuously held TFT and ULSICs versus TFT Symposia series, and is a fellow of Electrochemical Society, American Vacuum Society, Material Research Society. And he has served on committees for IEEE and other professional societies, as well as the president of the Electrochemical Society during 2018 to 19. Among many prestigious professional, industrial, and academic honors he received, he is the recipient of the biennial Edward G. Acheson Award and Gordon E. Moore Medal for ECS. He was an EDS Distinguished Lecturer, and on behalf of the organizers, I would now like to invite Professor Kuo to kindly share his screen to deliver his talk. Yeah, Professor Kuo, can you hear me? We cannot hear you, Professor Kuo. We can see your slides. Maybe you can just share your screen and unmute yourself.
Can you hear now?
Yes, I can hear you now.
Okay. Okay. Should I start now?
Yeah, maybe you can just share your screen.
Okay. I'll share the screen. Can you see the screen?
Yes.
Okay. Good morning or good afternoon. My name is Yue Kuo, Y-U-E-K-O, from Texas A&M University. It is a pleasure and honor to be able to participate in the celebration of the 75 years of invention of transistor. And my talk today, the topic is plasma-based thin film technologies in fabrication of nano to giga-sized electronics. The outline of the talk is first, I'll very briefly discuss what I mean nano and giga-sized electronics. Then briefly review the fundamentals of plasma-based thin film technology. Then I'll give you examples on the critical fabrication issues in the nano and giga-sized electronics. Specifically, I'll emphasize on the giga-sized electronics, and where the nano dimension, the material and physical properties are important. 3 examples will be given. One is the plasma CVD used to prepare the device. We emphasize on the bulk and interface properties that control the device characters. The second example is plasma etching in defined fine patterns. Again, we'll emphasize the uniqueness of the giga-sized electronics and compare with the nano-sized electronics. And third example, we'll use example of sputtering deposited ultra-thin high-K gate dielectrics and the non-volatile memories based on this kind of high-K dielectrics. And those 3 technologies which I mentioned are basic used in production today. So we are talking today, all the technology for plasma are for practical mass production of electronics, not just pure in the research or development stage. Then I'm going to give you some examples on applications of using plasma to solve some long-term problem based on the think out of box the approach. And at the end, I'll give a short my view on the future development of this technology. When we talk about nano and giga electronics, basic nano we're talking about is MOSFET in the IC, because the IC is in the stage we are in the nano-sized device. While giga-sized electronics, we're talking about TFT array, which is in large size. And how big and how large the gig size, which I'll have an explanation in the next slide. Because the IC and TFT-based display panel display are the 2 largest electronics industry today in the world. This left figure shows a diagram of the market value increase with time for IC and TFT LCD. As you can tell, it's drastic change. For TFT LCD, actually, in the year 2027, the market value was predicted to be $270 billion per year. And IC is several times larger than that. So for the IC, we all know there's a Moore's law. And the industry development has followed the trend for many, many years. Even there are people predict the Moore's law will be end. But there are also many discussions about Moore's law has not ended and will not end for a long time. For the Moore's law, we are approaching the IC for MOSFET part are in a small geometry, in a nano size. And for the IC, the quality of film are usually very high quality. High quality means low defects. While another area which we observed in recent years is people didn't pay attention too much, but it's in the practical words, it's obvious. That is, as we approach Moore's law approach smaller size, we are at the same time increasing the substrate size. For example, substrate means wafer for IC. For the TFT display is glass. Actually, the size increase with the year almost linearly, very similar to Moore's law. And the increase rate is about 30% per year. And from the first stage production until nowadays. And there is a general trend we observe, that is, for the IC, even people talking about 18-inch development, but seem to be 12-inch now. We are stagnant in the 12-inch for quite a few years already in the production. For TFT production, also similar phenomenon happens. From generation 1 to generation 10 to the 10.5, or generation 10, the size is about a 3 meter by 3 meters glass substrate. Also has been stagnant for quite a few years. But anyway, before we reach stagnant, the growth substrate size is about 30% per year. So that's all for the purpose of production. And IC, we all know, this short example, in 1956, the first IBM had memory, have hard drive. It shows in the diagram. That time was big news. It's 5 megabyte for 1 ton. The rest is history, as we all know. In the year 2000, commercially, we can buy hard drive and made of 40 gigabyte, about 4 ounce, the size about the CD. And 2007, then we have solid state USB drive. It's 8 gigabyte. And today, in the commercially market, you can easily buy a 1 terabyte USB. All this become possible is thanks to solid state, and also means the invention of transistor. On the other end, for the display, the 1989, the largest commercial display, CRT, is about 300 pounds. This 300-pound size is very deep, 26 inch in depth, so it's bulky. And because of the weight, people buy this kind of TV need to buy an extra stand, about $500 that time, to support it. That's 1989. And in the end of 1989, 1990, the world's largest direct view TFT LCD was introduced into production. And it's 10.4 inch TFT LCD in the IBM ThinkPad. That time, there was the largest display, direct view TFT LCD display. It cost more than $2,000 at that time. For PC, before printing time, $6,600. But even that high price that time, 1990, there are more demand than supply. After that, the TFT production progressed drastically. This diagram picture shows in the 2023, this year, in February, and in the US supermarket, you can buy 86-inch TFT LCD at a price less than $1,000. So this drastic change of display from CRT to TFT large size, also thanks to the invention of transistor. In this specific case, it's thin film transistor. For the IC, we all know production starts from wafer, 12-inch wafer. The wafer, we cut into many small dies. Each die, for example, in here, this case, is a painting chip. Each die is composed of many, many transistors. The commercial chips usually contains, one die contains about 500 million transistors. The transistor MOSFET. On the other hand, for display, the substrate is state-of-art is 3 meter by 3 meter. I'm talking into production, today's production, 10.5 in generation or 11th generation. The substrate is glass, 3 meter. The 3 meter, we are also made into dies. Each die is a one display. While one display is composed of many pixels, and out of the pixel, the key element is a thin film transistor. So this thin film transistor and this thin film transistor, next slide we're going to talk about, are based on same operating principles from the same origin. However, for product to work, or individual transistor works, or individual pixel works, and it doesn't matter, it doesn't work that way. You have to connect it, all the transistors with interconnect lines. So then the product can be working. For display, the same. Each pixel transistor, simple transistor, we have to connect with metal lines. The difference from interconnect line here, in the IC, for example, state art is copper. And because the size, a chip in the side about inch by half inch, roughly the size, then interconnect copper had to be stacked up in 11, 12, or even up to 15 layers. The copper interconnect multi-layer. And small size copper line is 0.5 micron, even less. While for TFT LCD, the line width typically are bigger. For example, a few micron, 10 micron, for example, seem to be wide. But however, the display size is so large, so the line had to be continuous through the whole display. So it's a very challenging work. Because the line width is a few tenths of the diameter of human hair, you make it as long as tenths of inches. And that's a challenge. But those interconnect had to work also before the product is available. And we first present this idea of these two technology in two different fields actually have something in common in device physics, common in device fabrication process, common in material issues, basic fundamental issues. So we presented in 2007 in a conference in AMFPD. Then we write down the paper in 2008 to generalize these two technology. And another technology based on the solid state, and we also report recently the solid state light emitting device. And this diagram picture shows the structure as I mentioned previously, from wafer to the die to cross section of a die where the transistors are on the bottom of wafer and the rest are interconnect. For TFT LCD or TFT based flat panel display, including OLED, etc., or micro LED, the display is based. The fundamental key element is a glass. On top, many transistors are made of, many pixels. Each pixel includes a simple transistor, and for LCD, usually have capacitor. So those are fundamental structure. Then we talk about IC, we talk about nano size. For TFT, we talk about giga-sized. While the MOSFET and the TFT are built based on same fundamental technology, fundamental physics. That's what the MOSFET concept presented in 1925. Then for IC, the progress are we all familiar with. The 1947 inventor transistor, and then gold silicon bipolar transistor, and the rest are history, the IC production microprocessor. While for TFT, the first TFT was realized in 1962, made of cadmium sulfide. Then shortly, the oxide TFT was reported. But those in the 1960s, if you look at old literature, in the 1960s, when TFT first reported, there was in this electric field, there's a big stir. That time, there were people in the TFT trying to claim they can take over IC markets. So there's a big fight there. As we can tell, the history proves it didn't succeed because silicon wafer-based technology is so strong. But TFT people didn't give up. They're looking for field application. In the 1973, the first TFT-based LCD was demonstrated, made of cadmium selenide. But again, the technology is not available for production. Until 1979, the first monosilicon TFT was reported. Then that time on, all over the world, as I remember, all the major electronic companies are jumping into this field, a monosilicon TFT, and into the production and develop a technology until 10 years later, the first mass production of large direct field, the 10.4-inch TFT LCD was produced. So 10.4-inch TFT array was first made into product in the IBM product ThinkPad. Then today, the technology based on that one expand the size, expand the quality and dimension of the display. And 2004, the first IGZO TFT was introduced. And those are history. So the nano-sized transistor and giga-sized electronics based on the same origin. During the process development, the TFT technology, the structure, because all the films were deposited, so there are various kinds of structure reported. For the IC, the structure will stick to the coplanar structure for a while until recent years when size is shrinking, then the FinFET get around, etc. structure was introduced. So for the TFT is based on same operating principle as a MOSFET, but the difference is this. For TFT, all the film was deposited, and usually at low temperature, because glass is used on the substrate. So glass usually cannot stand more than 400 degrees C, typically less than 350 degrees C. So the film deposit, and it's very different from silicon film. For example, semiconductor itself is full of defects. The defects are charge trapping side, traps. For example, for polysilicon, the trap is a defect in the grain and a grain boundary. For amorphous silicon, the traps, for example, in dangling bond. For oxide, the traps are oxygen vacancy. So during the operation, apply gate voltage. First, the trap have to be filled. After traps are filled, then conducting path was formed. Then the transistor turned it on. So this shows the three major production technology TFT, the transfer characters. And the operating principle here, TFT, is a little bit different from MOSFET. This is based on accumulation of electrons operation. But MOSFET is from depletion part. Otherwise, the performance, the principle are similar. So I want you to keep in mind because the low temperature deposit film will have defects. Although the defect control is important for the operation of transistors, the TFTs. And we are talking about the technology. Today, I'm talking about the technology is production technology. For production technology, any new device, new material process, when introduced into production, we had to satisfy all the requirements. The device performance first, electric characters or sometimes optical characters had to satisfy, and reliability had to be satisfied. And any new materials introduced had to be compatible with the existing materials. Any fabrication process, conventional fabrication process, which lists here, CVD, sputtering, plasma, etching, implantation, etc. Those processes, key element is this. Any production process, you need to satisfy three key basic element requirement. Large area capability. For IC, you have to be able to use in a 12-inch minimum product size. And you have to have a low thermal budget. You have to have a high throughput. So those are fundamental requirements for any production process. So fortunately, semiconductor plasma-based process can satisfy all the three. That's why plasma process is applied in both nano-sized MOSFET and giga-sized TFT array. So plasma process Here, this diagram shows a simple diagram for those who are not familiar with the technology. Basically, we have two electrodes. Electron inject from one electrode to the other while heat the feed gas. During the feeding gas heating, and the reaction happens because electron usually contain the electron temperature is pretty high, even the electron density is low. But once heated molecules, the feed gas, there are series of reactions: excitation, dissociation, attachment, etc. So it's a very complicated process. And during the process, light is emitted. So we have we see the plasma light emission. We can take emission spectroscope. From emission spectroscope, we can identify a major component in the plasma process. But basic plasma process includes two components. One is ion charged, such as ions. The other one, neutrals. It's very complicated because neutral can be molecules, atoms, fragment molecules, free radicals. So those highly reactive elements are responsible for the thin film deposition and etching, which is different from conventional chemistry. So in this process, we are talking about non-equilibrium thermodynamics. So the conventional chemistry we learned, the equilibrium thermodynamics does not apply here because a lot of quantum reaction occurs. So this is a chemistry part. Another important part in the plasma, there is a potential, plasma potential. Because plasma potential is higher than the potential on both electrodes, so the ion bombardment are driven by plasma drop. So the ion bombardment, because plasma drop, potential drop from plasma to electrode, are affecting the surface reaction. So that's a very simple process. So the three major processes people use in production: plasma etching, reactive ion etching, plasma CVD sputtering, are based on the same principle. The major difference is for plasma etching, RIE and PECVD, the substrate are immersed in the plasma, means located between two electrodes, while the sputtering are generating plasma near the target, where the substrate bias is high. Is a plasma potential to the target bias is very high. We talk about 1,000 volts, for example. They sputter the target, then the fragment or radicals, etc., moving, flying to substrate surface to deposit it. So the etching and deposition, it depends on surface. If the plasma element react to substrate, form volatile product, we call the etching. If react element from plasma react to substrate surface deposit, we call the plasma deposition. Those are the fundamental plasma process, two electrodes. Then people do use the ECR, inductive coupled device, to introduce actual free radicals into the plasma phase to make a density of radicals or higher, so enhance the deposition or etching. So that's a basic principle. So when we use this technology to do IC and to make a TFT, this picture shows an example of IC cross-sectional structure. This shows the TFT structure. For the plasma CVD, it's used in both IC and TFT. But for IC, plasma deposit film are used in the interlayer dielectric or passivation, mainly not in the device area, such as gate dielectric or semiconductor layer. For TFT, the film is used in the semiconductor layer and gate dielectric. For plasma etching, as you can show the different configuration, IC is used to etch lines, provide vias, provide a trench, or usually in the nano dimension. to nowadays the product. For TFT, it's not in the null dimension. It's provide long line, not vertical, and actually sloped, and involve many unique materials. This one shows example for display for TFT, and because structure is gate dielectric is deposited on gate, then subsequently we deposit different layer. So step coverage is very important. To provide conformal step coverage, usually the gate metal has to be sloped, which is very different from the IC. And also, for example, one of structure for bilayer structure, the N+ doped layer had to be etched selective from the intrinsic silicon layer. So we need high selectivity. And this is the first report of obtaining selectivity more than 1 for N+ to amorphous silicon. So that one enables the mass production of bilayer structure of TFT. And another unique is for TFT, the metal gate, for example, usually made of metal. To make it highly reliable, the dielectric usually can be several layers. And for metal layer, people anodize it to make sure it's totally covered. Then deposit a separate gate dielectric layer. For contact, the metal oxide had to be etched selected to expose the metal. So this result shows then it can be achieved with proper planar chemistry. So those are unique examples of unique part of the TFT in the production, use the planar etching technology. And another unique part of planar etching of TFT is for example, the last stage HM+ layer, and there is a phenomena called planar radiation damage. The transistor after the last step deposition actually have high threshold voltage, high leakage current. And for wire, it's what unknown where it come from and why we have this kind of issues. It become production problem because it's on-off problem until we clarify that's caused by radiation damage from planar etching. This damage can damage surface, for example, dielectric passivation layer on the channel passivation, and also can cause damage. ESR shows the damage of bulk layer. So this interface and bulk layer damage cause the TFTs behave over large threshold voltage, high off current. Fortunately, this damage can be repaired by a simple annealing step. So the planar radiation damage is unique, which does not observe in the IC. In the IC, planar damage usually are because the thin gate dielectric breakdown and during planar charge neutralization. But for TFT, because gate dielectric is very thick, so that phenomenon didn't happen. But the radiation damage happens. And this can be even confirmed with a good transistor. We shine the UV light, for example, argon laser double frequency exposed TFT. You can see the performance, exactly like the after planar etching damage. Then after that damage, we can anneal repair to the original condition, the good transistor. So the next example is planar CVD. In this example, planar CVD and people in the early stage for production, if you go to 10 companies, they have 10 recipe of deposit thin film, for example, gate dielectric. Most common is silicon nitride. All of them works, but none of them are similar, and no one knows why, because those are from experimental data. And until we did publication correlate the process to material to device relationship, then it becomes clear. That's the planar CVD deposition of silicon nitride there is a critical power. This critical power is the maximum power and can be applied to achieve the highest deposition rate. And that critical power affect the refracting index of gate dielectric. That can be further monitored on the film properties. For the SiH NH bond, you can tell power increase, SiH is decrease, NH bond increase. So further on, then the stress of film change from tensile stress to compressive stress, from the low power to high power. So in other words, the process can be directly related to mature properties. And those mature properties further can be correlated to TFT device performance. In this case, shows no matter what your process condition, and eventually there is optimized mature properties for the best transistor performance TFT. In this case, the refracting index of silicon nitride gate dielectric is between 1.85 and 1.9. That gives the best threshold voltage and most reliable device. So this gives very simple guideline. So from process, we can tailor towards the optimum device performance. So this relationship actually has been widely used in the industry in the develop a new process. And the reason the deposition rate condition can affect film quality, can affect device performance is because the plasma CVD is a unique process. Process CVD deposit film because the radical formation during dissociation of silane ammonia N2. But people neglect one thing. During dissociation of the molecules, then hydrogen are generated. Hydrogen is important to pacify dangling bond in the, for example, gate dielectric. But however, hydrogen when it's high concentration at high power, it's high ion bombardment energy, it becomes etching. It can damage the surface, can remove the passivation hydrogen, cause dangling bond formation. There's a reverse the refractive index and cause the threshold voltage increase. So this is the etching deposition phenomena. That's can be used to explain the whole process condition to the device. And that result, we can further use to answer a question for that bothered the field for a long time. That is, for TFT, among silicon TFT, bottom gate is better than top gate. That means the film, gate dielectric, and semiconductor layer is deposited in the same condition, just reverse order, then results transistor different. If gate dielectric deposit first, then semiconductor deposit, the transistor is better, low leakage current, better performance than reverse order. And this one is because the etching deposition process. Because the nitride, the gate dielectric deposit usually more harsh environment. And silicon, amorphous silicon is less harsh environment. So when you have a harsh environment deposit film first, less harsh environment, less harsh condition deposit, then transistor, the interface is less damaged. While if you reverse, the channel interface will be damaged. Then that causes poor device performance. The third example is a sputtering deposit of high K dielectric. And high K dielectric, conventional people use CVD or LD. Actually, CVLD deposit metal oxide for high K. There is a common problem. For example, hafnium oxide, its crystallization point is low, it's 600 degrees C. So for the device fabrication, the temperature usually is higher. The crystallization of gate dielectric will cause reliability problem. So we report in the late 1990s that we use doping method, add the element into the metal oxide, then you can see the increase of the crystallization point by a few hundred degrees. So then keep the gate dielectric in the amorphous shape up to, for example, 900 or even above. So the doping process, we can even deposit high K with sputtering. Because of doping, we change the interface characters. The interface actually high K, for example, here we use the zirconium dope hafnium oxide. They form an interface layer. This interface layer is hafnium silicate. It's not a silicon oxide. So interface itself is high K. And that's demonstrate the SCAR. And this kind of device, we can make into EOT less than 1 nanometer. So sputtering can be used to deposit gate dielectric with EOT less than 1 nanometer. That's another example. Then based on that one, we keep it amorphous shape for high K dielectric. Then we can embed it another layer. Then we use rapid thermal linear to heat it up the high K with embedded layer. Then we form nano dot, nano crystal embedded. So in that case, it becomes non-volatile memory. The charges are injected into the gate dielectric and retained there. And the retention can be more than 50% after with bias stress for extrapolate to 10-year equivalent. And embedded metal, there are many kind of layer we can deposit materials from different nanocrystal. This nanocrystal shows if no nanocrystal, the high K has no hysteresis, no charging. But nanocrystal, if we embedded a different material, we can make it prefer to trap electron or prefer to trap holes. So in other words, we can embed the nanodot materials to separately store electron and holes. And those are all done by sputtering method. So those are in the manufacturing process, using manufacturing equipment. Then for the beyond the manufacturing process, and high plasma technology can use to solve some long-term problem, which I'll give a couple examples. First, copper etching by plasma, and it has been 60 years since we first introduced semiconductor fabrication, and people had the idea of etching copper with plasma. It doesn't work. Very simple, because the conventional wisdom of etching copper is form volatile product, but copper halide or organic compound has low vapor pressure unless you heat up at high temperature. This bothered the field, the production for 60 years, until IBM introduced the CMP, chemical mechanical polishing. That's widely used in industry. But this process, even used in industry, then it's a very tedious process because it involved several steps: trench etch, sputter deposit, and electropolish deposit, a barrier layer, seed layer, and electroplating of copper, then followed by nanoparticle solution, involves the electromechanical polishing, and involve the wastewater treatment. And this process, endpoints is difficult to detect, and dishing is a serious problem. So in the field, basically, people work for so many years, impossible etching, until a few years ago, we report we can do it. But actually, copper can be etched with all existing equipment in the semiconductor field, in the production facility for many, many years. And what we showed is, just like aluminum, copper is photoresist pattern, then exposed to plasma of chlorine or bromine. The copper will react with chlorine for copper chlorides. Those chlorides are polycrystalline. And the conversion of copper on the exposed area are at high speed, for example, a few thousand angstrom per minute, even at room temperature. The whole layer is converted and stopped at the barrier layer. So selectivity is infinite to 1. Then this layer is dipped in the HCl solution, is infinite solubility, instantaneous dissolve, then we form a copper pattern. So we report in the late 1990s. Then after that, we did a reliability test. We used a method to etch copper on the step. So with proper control polymer chemistry, we can avoid the cusp formation. And those kind of lines with on the flat surface or on step surface, electromigration phenomena is the same as conventional metal electromigration phenomena. Then the ferromagnetism is from the void formation and propagation. So this technology has been used in the 15-inch TFT LC production in 2008. And it has also been demonstrated in integrated circuit, TIs by CMOS chips, and IBM test pattern. We have about 0.3 micron lines. So copper line actually can be etched with copper plasma at room temperature using conventional parallel plate reactor. And every company has a facility, every company has equipment. Just the reason people cannot solve problems because they are thinking the wrong way. And further on, our recent work shows oxygen can even replace chlorine because chlorine is corrosive, is undesirable. So if we use oxygen, we can do the same reaction, convert the copper to copper oxide, then strip with HCl, form copper lines. So that's further one step improved for making it more user-friendly production because oxygen has plenty of supply at low cost and environmental friendly. And for copper interconnection, as we all know, recently there is a study shows that copper when make into fine line, there is the issue come out. Resistance become very high, and the electromigration life had a problem. So we further introduce a ruthenium as a barrier layer for copper. So the advantage of this one is copper can be etched by oxygen. Ruthenium also can be etched by oxygen plasma. So the whole new ruthenium copper stack for interconnected line, we use the oxygen to etch, and electromigration shows a high reliable because ruthenium electromigration life is longer than copper. So this kind of structure has long lifetime. Ferromagnetism is similar to conventional interconnect metal. So since oxygen we can use to etch copper, then another application we introduced recently is the copper usually exposed to air will form native oxide, which is undesirable because it's porous, it's poor quality. However, use oxygen if we can, under controlled condition, expose copper to oxygen plasma, form a thin oxide on the surface. Then the lifetime, the electromagnetic life is not deteriorated compared with pure copper. But the advantage is under electromigration condition, because the copper under high current density electromigration, copper will diffuse out. And in the conventional, copper will diffuse into the adjacent dielectric and cause reliability problem. However, if we have a thin oxide formed by plasma, then during electromigration, copper diffused through the thin oxide or scattered because copper form oxide, Cu2O oxide. So that case, it's scattered there before it can diffuse into dielectric. So the help for interlayer dielectric. Last example which I'll give is for the sputtering deposit, the light emitting device from silicon. The principle is this, very similar to transistor invention, come from vacuum tube. The Edison style light bulb today is not much different from 140 years ago when it's invented. The filament are emit light from current path at high temperature under vacuum condition, but the lifetime of vacuum tube is low. when we made it into the solid state light bulb, so vacuum is replaced by dielectric. In the dielectric, we form nano element. So then by applied voltage, the nano elements are excited to emit light from Planck effect. And this kind of light emitting, for example, 300 micron device is composed of thousands, tens of thousands elements. Each element is a nano device. So it emits light in the visible wavelength, actually very similar to sunlight. The CET shows its warm white light, and good for lighting and many other applications. And this kind of device has long lifetime of 20,000 hours and under operation in air without any passivation. It's more than 20,000 hours. And after several PhD student graduate, we stopped the testing because it's still running. So to summarize this talk, the semiconductor transistor-based solid state, we are trying to match the ultimate challenge is human function. Currently, transistor can do almost all the major functions human being can do, from brain CPU function to test sensor and to display, etc. And those functions, the key element is CPU. We can take as currently is IC, nano-sized transistor, control the technology, and the rest function can be done by TFT, and all controlled through the interconnect lines. So today, current copper. But we believe the transistor can be applied beyond the human function, which is light transmission. Then solid state, human beings, we cannot emit light, but solid state, we can emit light. So I believe the ultimate goal is use solid state to generate light and transmit signals through light, and hopefully, ideally, can operate products through light processing. And that will be the next 75 years, hopefully, you can see the result. Now, I'll summarize the talk. Basically, 2 points. One is plasma process is critical production technology for the nano to giga-sized electronics, because the plasma process can satisfy requirement on low temperature, large area, high throughput. And we foresee plasma technology can be even further used for future nano giga-sized electronics, taking advantage of the nature of a non-equilibrium thermodynamic reaction in the plasma process to create a new device and new materials and new structures. And I'll stop here. This is acknowledgement to all of my students, postdocs, and the sponsors. I'll stop here. Thank you.
Thank you very much, Professor Kuo, for enlightening all of us about from nano to giga. And there are a few questions which have been shared by the attendees in the chat section. I shall share my screen so that everyone can see these questions. I hope it's visible to you also.
Okay, the first one. When we discuss metallization level on the order of 50 or higher, and how do we address thermal dissipation issue? That's a very good point. Actually, you're asking the question of a 100-year-old problem. And thermal dissipation, for example, IC is a problem, is difficult to solve and is still ongoing. I think the general people approach thermal dissipation is, for example, by applying material with high thermal conductivity, hopefully to conduct current from the inside to the outside, then through the air cooling or water cooling or liquid cooling to solve the problem. And currently, so far, I do not see the fundamental way to solve problem. And the people had to use a method, use a device, electron device, and try to remove the heat. But I think it's still quite the distance from practical application. I hope I at least partially answer your question.
Yes.
And the second one, what are the challenges or limitations of plasma-based thin film technology? The challenge is this. As you can tell, plasma-based thin film has an advantage of because it's not restricted by thermodynamic limitation, the conventional equilibrium thermodynamics. So we can create new materials which do not exist in nature. For example, silicon nitride or gate dielectric or amorphous silicon. And I show the examples, and I can give you my first-hand information. When we make a transistor at 250 degrees C, amorphous silicon transistor, and use the silicon nitride, those nitride are non-stoichiometric. So not Si3N4, actually Xi3N more than 4, slightly nitrogen rich. And amorphous silicon and has high hydrogen concentration. Those films do not exist in nature, but made by plasma. But those kind of devices are stable because it's made at 250 degrees C. So we store the transistor at room temperature for almost 30 years. Today, I take the transistor today to remeasure it, still works, just like original. So that's the amazing part of the plasma-based process. And the people most common complain about plasma process is this: the equipment is expensive because it's vacuum technology. So, but plasma generation in the vacuum is currently the best way to provide materials. So if you have some way to generate plasma and with a low cost, and low cost means if you can eliminate plasma, the vacuum is good. But remember, vacuum has the advantage of high purity. We have high vacuum, high purities, and the good control quality of materials. And any way to eliminate vacuum, you have to think about the quality of film, the contamination, the control of the properties. And that's my view on the challenging of plasma-based thin film technique. The next one is, does plasma trees introduce defect or surface modification to the thin film layer of TFT? How does it affect device function? That one I just showed the example. For example, for the amorphous silicon TFT, for plasma radiation damage, for you etching the film, you damage the layer on the surface, where we show the surface composition change, the bulk film ESR signal changes. So those are films, and because the TFT deposited by plasma at low temperature full of defects, the dangling bonds are passivated, but the weakly passivated. So radiation can damage it. And fortunately, those damages are not caused the looser device. For example, dangling bond, hydrogen passivation bond broken, but it didn't lose. It's still adjacent to it. So with a annealing step, we can reabond, reattach it, then recover the performance. So that's the plasma damage, the unique part for TFT. And next one, how does one determine the ratio of gas for plasma generation that will be used for specific fabrication process such as etching, apart from material compatibility? Okay, that's interesting. Then I mentioned a plasma process. The chemistry part is very complicated. Currently, there is no single theory can will predict the complicated reaction. Simple thing, CF4 plus oxygen, people have used for 50 years. And because the reaction is non-equilibrium thermodynamics, for example, the molecules are bombarded with electrons, tear apart into radicals, ions, etc. Then the radical ions and react with another component, radical ions, and on the surface form product. So it is a predict. So very difficult or almost so currently there's no good theory to explain to predict it. So in this field, most are by experiment. But fortunately, most experiments related to silicon process have been carried out and with large amount of literature. And you can show in the literature search. For example, for silicon H, you CF4 plus O2, you want Jan fluorine, which is effective etching silicon. And usually O2 concentration, and typical talk about, for example, 10%. When you can use the emission spectroscope to actually see the fluorine concentration change peaked at this around that range of concentration. So that is emission spectroscope is a very powerful tool for monitor plasma chemistry. People do use a mass spectroscope, etc., but it's more tedious. Emission spectroscope, then you can get a pretty good idea what the plasma gas effect on the plasma chemistry, on the radical formation at least, or some ion formation. The fifth question, in one of the slides, you mentioned that the electron temperature reached 10 to 4, 10 to 5 Kelvin. What is the significance of such a high carrier temperature? The electron has to heat molecules to dissociate it. So in the typical plasma, the plasma we are talking about here we call it cold plasma. Actually, the 10 to 4, 10 to 5 K is typical in the plasma etching or deposition condition, the temperature. And the temperature that high, remember, electron are very small mass. You have high energy because of high temperature, the heat molecules, that's enough to break down the bond or attach the bond and to form various composition. So the temperature, when I mentioned 10 to 4, 10 to 5 from literature, actually remember electron temperature distribution is a distribution, not unimodal. It's a distribution. So when the distribution of energy of a group of energy, electron with the distribution different energy, and in this temperature range, heat molecules. So when high energy part can split, low energy part doesn't work. So you just lose the function. So that's a plasma part for the temperature. And I hope I answers your question.
Yes, thank you very much, Professor Kuo, for taking up all possible questions which have been shared by the attendees in the chat. Let me just check if there are any more questions. No, I cannot see any more questions in the chat now. Okay, on behalf of IEEE Electron Device Society, Delhi chapter, and my other co-host organizations which have been part of organizing this particular webinar series, I would like to thank you and to all the attendees who have been there with us for this particular session, and hope to see you all again on the upcoming session, which is scheduled for June 19th. You'll get a Zoom reminder for the same. And stay connected, and let us all enjoy the glory of the 75th anniversary of the transistor invention for the year 22 and 23. Thank you very much, Professor Kuo.
Thank you.
Thank you. Thank you.